Okay. So this entire learning procedure. So what you see that what we have mentioned that the procedure works in this way, that in a particular switch, whenever you are receiving certain signal, you convert it to the bit pattern, and once you have converted it to the bit pattern, you construct the frame. Then in the frame, you check the destination MAC address. I am writing it as D. After checking the destination MAC address from the incoming packet, what you do, you make a match of this destination MAC address with the MAC address of the switch or the MAC address of that interface. Well, now, if there is a match, then you accept that packet, otherwise you drop that packet. That means you see that for every packet that you are receiving in a switch, you need to actually do this processing. You need to construct the frame, extract the destination MAC address, make a matching of the destination MAC address with own MAC address, and accordingly decide whether to accept the frame or not. Well, now this procedure needs to be very fast because you are receiving millions of packets in a machine, and many of those packets may not be intended for you, rather it is intended for other machines. So that's why we apply a kind of optimization in this particular procedure, and that is basically called cut-through switching, or sometimes it is also called wormhole routing. So what is this cut-through switching? That the cut-through switching is a functionality which is implemented in hardware. That means once you start getting the bit stream, decode them immediately based on the MAC frame structure, and that is actually interesting. That is interesting in the context of how we organize the MAC frame structure. So if you look into the MAC frame structure, it contains some initial bits. Those initial bits are called the start frame sequence. So the start frame sequence, these bits are used for identifying the starting of a frame. Now, once you are getting the starting of a frame, then the immediate next set of bits are the destination MAC address. So we put the destination MAC address first, and then we put the source MAC address in the MAC header. And here is the reason for that. So what you do, that as you are getting the individual bits from this frame, so you get the initial start frame sequence, which is a known set of bits. So the purpose of the start frame sequence we'll discuss later. After that, you get the destination MAC address. The bits correspond to a destination MAC address. And once you are getting the destination bit of the destination MAC address, you start immediately doing the matching. Okay. So that way, if you find out that well, some portion of this destination MAC address is different. Say for example, your MAC address is something like 11001010. That is say your MAC address, and you see that the destination MAC address is 11001110. So you make a, so once you get a 1, you take a match, there is a match, then next one there is a match, next 0 there is a match, next 0 there is a match, 0 there is a match, 1 there is a match, and then you see there is a mismatch. Okay. In the receive packet it is 1, and in your destination MAC address it is 0. So the moment you find out such a mismatch, immediately you discard the frame. Okay. So that way you can actually speed up that entire procedure. So this particular procedure is known as cut-through switching, or also sometimes known as wormhole routing. So this is to speed up the processing of the frames at the MAC layer. So that is the kind of first part of implementing a kind of the switching functionality. That means applying an intelligent way to make a mapping with a destination MAC with the corresponding port address to understand that in which particular port to forward a packet if there is a match in the destination MAC address. And the second idea, which was there, it is called the spanning tree switches. Okay. So the idea of the spanning tree is something like this. So the idea of the spanning tree is that to increase reliability, redundant links may be deployed between the switches. Well, this creates loops in the topology. Well, now, as we have seen earlier, that for unknown destination, the switches flood the frames. Now, if you do not apply any kind of mechanism, those flooding data, the data that are the frames that are being flooded, that will loop within the NAND. Okay, so here is an example. So, for example, H1 wants to transfer a packet to H2, and you really do not know that where H2 is connected to it, in which particular switch H2 is connected to it. So, whenever you are sending the frame to S1, S1 will start flooding. Okay, so S1 will send it to its outgoing interface S2 and S3. Now, once S2 will receive it, S2 receive it from S1, so S2 will forward it to S3. Okay, now S3, whatever packet it is receiving from S1, it will forward it to H2. Similarly, whatever it has received from H2, it will forward it to S1. That way, the frames will loop within the switches, and we need to break this kind of loop. Okay. Now, to break this kind of loop, the approach which is being taken is to construct a spanning tree across the switches. So here, in these solid lines, they are the part of the spanning tree, and the dotted line are the other links. So we construct such kind of spanning tree over the switches, and whenever the flooding is used to send the frames from one particular machine to another MAC address which is currently unknown, that which is unknown to the switches about in which particular port it is connected to it, it uses this spanning tree to flood the frames. Now the spanning tree algorithm works like this way. The switches run a distributed algorithm to build a spanning tree. Each switch periodically broadcasts a configuration message. So if you capture the packets using WordShark, that you see that you will receive multiple different packets corresponds to this spanning tree protocol or STP. So these are the kind of configuration message which are broadcast out of all of its ports. It is processed, the switches process the message it receives from other switches. Well, so these messages, as I was mentioning, they are embedded in the STP frames, and if you capture the Ethernet frames using WordShark or speed up, you will see that multiple STP frames are there. Now, initially, you need to choose the root of the spanning tree. Now, to choose the root of the spanning tree, the switches include an identifier based on the MAC address in the configuration message, as well as the identifier they believe to be the root. Well, so they basically either they choose one, every switches independently choose one node as a root, or they designate themselves as the root. Then the bridges choose the bridge with the lowest identifier to be the root. So among all the different switches which are there, switches or bridges which are there, among them the switches which contains the lowest identifier, that work like a root. Then a tree is constructed, a tree of shortest path from the root to every switch is constructed. It includes the distance from the root in the configuration message itself, that in terms of number of hops, ideally. Now each switch remembers the shortest path it finds to the root. The switches then turn off ports that are not part of the shortest path, and this algorithm continues to run to detect any changes in the topology and update them. So the overall protocol is something like this. Say you have multiple switches which are interconnected. You can just think of the switches as a network graph. Okay. So assume that these are the network graph of the switches. Well, now say I put up individual identifiers to the individual switches. Okay. Now, what happens that every switch starts broadcasting this configuration message. Okay. So S1 starts broadcasting an HTTP packet, S2 starts broadcasting an HTTP packet. So initially, when S1 is broadcasting the HTTP packet, S1 has not observed others HTTP packet and it finds out that it has the lowest ID, so it puts itself as the root. Now when S1 say receives the HTTP packet from S3, assume that the minimum of S1 and S3 is S3. If that is the case, then S1 updates its route to S3 and again rebroadcast the HTTP packet with S3 as the root. Well, I'm mentioning that from S3 it has in one of distance. So that way the messages are getting propagated, and after some rounds of message propagation, every switches is able to know about what are the other switches that are connected. So typically what it does that when it observes that there is no update in the received HTTP packets for some consecutive routes, it believes that it has reached to a kind of consensus. And at that stage, it finds out that among all the IDs which are here, which is the lowest ID, and it assumes that lowest ID to be the root of the spanning tree. Well, and then every node computes the minimum distance from that root. So assume that in this HTTP packet broadcast, everyone finds out that S5 is the root. Now, once they finds out S5 as the root, then S3, S4, S6, S7, they connect to, they directly, S7, they directly get connected to S5. They are in the one-hop distance, then they broadcast the information. Then S1 gets connected with S3, S2 gets connected with S4, S6 gets connected with S7, and that way the final spanning tree is constructed. Now, there is an interesting story about this spanning tree algorithm. So this spanning tree algorithm actually came very later, so that is very interesting. So this spanning tree algorithm was invented in 1985. So you can see that by that time actually TCP was also got invented. Right? So that means the network designers they found out this problem much later when they started connecting multiple different switches or multiple different LANs. Using multiple different switches and putting up redundant part in that switches. So this spanning tree protocol, it was invented by Radia Parman. Radia is sometimes also called as the mother of the internet. So Radia, when she was just facing this particular problem, and she thought of that, how to solve this problem, and to solve this problem, she actually written a nice poem on a piece of paper, and that actually became the algorithm for the spanning tree protocol, and that poem itself became the proof of the algorithm invented for the spanning tree protocol. Okay. So the poem is nice. I think that I shall never see a graph more lovely than a tree. A tree whose crucial property is loop-free connectivity, a tree that must be sure to span so packets can reach every LAN. First, the root must be selected, by ID it is selected. Least cost parts from root are traced, in the tree these parts are placed. A mesh is made by fox like me, then bridges find the spanning. So this is the kind of poem that she written to express the spanning tree protocol which she invented. So that was the kind of spanning tree protocol. Now, one interesting fact which is there in the internet that you might be confused upon is the different kind of devices that we are talking in the internet. So we are talking about the router, switches, bridges, repeater, hub, gateway, and all these things. Now, these different devices actually work in different layer of the protocol suite, the TCP/IP protocol stack. And here actually I have just tried to put up the name of the devices which work at different layer of the TCP/IP protocol stack. So in physical layer we have repeaters or hub. So the purpose of the hub is very simple. The purpose of the hub is basically to interconnect multiple different LAN segments together And hub works in a very simple way. Hub doesn't have any kind of intelligence. So what hub does, that whatever signal it receives in one input, it simply copy that signal to other input without making any changes. Okay. So that way hub just repeat the signals and the repeater, it is a bit different from hub. But the purpose of the repeater is to increase the length of the wire. So I think you have already also seen the repeaters while roaming around our campus. So when roaming around our campus, you will see that wires which are there on the trees that connects the entire land. So you will see that some devices are hanging which are like this. Okay, so they are actually connected like this. You get a wire which goes as an input and another wire that goes like a airport, and this device is hanging somewhere in between. Okay, so if you just watch the network wires, you can see such kind of devices which are hanging. And these devices are typically a repeater, and the purpose of the repeater is that whatever signal you are getting, so typically this signal strength get reduced as it gets propagated on a medium. Okay, so in wireless, this kind of signal quality drop is much more compared to the wired media, but even in a wired media, the signal strength get reduced as it gets propagated. So the purpose of the repeater is actually increase the strength of the signal. So it reproduces the same signal but with higher power. Okay, so that you can transfer the signal further. So these are the two devices which we widely use in the physical layer, the repeaters and the hub. Then in the data link layer, we have the bridges and the switches. So typically, we call it the L2 switch when it connects multiple different LANs of same type. We call it as a bridge when it interconnects different LAN of different type. So for example, a bridge between the Wi-Fi and the internet. Then in network layer, we have the router. Sometimes we also call as the layer 3 switch or L2 switch. Then at the transport layer or the application layer, we have the corresponding transport layer gateway or the application layer gateway. So the gateway devices we can. So that way different physical devices are deployed at different layers, which operates at different layer of the protocol stack to support the kind of network functionality. Okay. Any doubt up to this point? Okay. Now let us briefly talk about another concept which is called a virtual LAN or VLAN. Okay, so I guess that many of you have heard about these VLANs, and I know that many of you are actually curious to know that what is a VLAN. I have received this question from a few of you about what is a virtual LAN or what is a VLAN. Now, typically LAN is a broadcast domain. So that we have seen earlier, that every frame is broadcast to all the machines connected to a switchboard. So a physical LAN is something like this, that typically we make the connectivity in this way, that with the switch, we connect a shared hub, and with that hub, we connect multiple different machines together. Okay. So all these typical machines are the part of a LAN. Okay, so here in this particular port, these three machines are connected via this shared hub. So this becomes part of LAN 1, then this becomes part of LAN 2, then this becomes part of LAN 3. Now, in many of our applications, what we want to do, that think of an organization of something like this, that these physical LANs are at different floor of the building. Okay. So we have the switch. With the switch, it is connected with the shared hubs at different floors of the building. And with that hub, multiple different machines, say H1, H2, H3, they are connected with one hub, and they constitute a physical LAN. Then H4, H5, H6, they constitute another LAN. Then H7, H8, and H9, they constitute another LAN. Okay, so that way different LANs are being constituted. Physical LANs are being constituted. But assume that I have different departments span across these different floors. Say for example, the account department. The account department is there in floor 1, floor 2, as well as floor 3. And these three machines, H1, H4, and H7, they are the part of the account department. Okay. Now that way, what I want to do that I want to logically interconnect these three machines, H1, H4, and H7. Why? So that I can create a logical broadcast domain, and in that logical broadcast domain, these three machines operate. So that way, I can create a logical LAN constituting this machine, say H1, H4, and H7, become part of a logical broadcast domain that we call as the VLAN. Okay, so that way I can have multiple VLANs which are through the machines from different physical LANs, but they logically be a part of a broadcast domain. Okay, so that means the purpose of the VLAN is to construct a broadcast domain even if the machines are not part of the switchboard. Okay, so for that we use something called a VLAN ID. So that way we do a kind of logical segmentation of the machines. Well, and the purpose, as I have mentioned, say for example for data security. That means the design policy such that only nodes in a VLAN can communicate with each other. I want to ensure that only H1, H4, and H7 should be able to communicate with each other. H1 should not be send any packet or any message to H2 because H1, H4, and H7 they are the part of say the accounts department and their machines are confidential. So that way we design such kind of VLANs. Okay. Now to do this, implement this VLAN, the VLAN ID is actually implemented within this tag field. Okay. In the Ethernet frame. So the standard Ethernet frame format that was standardized in IEEE 802.1, 802.3 Ethernet that did not have this tag field, which was for the VLAN ID. Then IEEE 802.1Q, it actually provided or incorporated the idea of the VLAN in the standard. So what it did that in between the source address and the type field, it inserted this tag bit, and this tag bit contained this VID, which is basically the VLAN identifier of the VID. So in the previous diagram, in the previous diagram, whenever I constitute a VLAN, I will provide the same VLAN ID to all these three machines, H1, H4, and H7. Okay. And that is given by this VLAN ID, which is a part of this tag field of the 802.1Q Ethernet header. Okay. And there are other management field like the canonical format identifier, the priority code point, and tag protocol identifier. These are the kind of management field which are being used in the VLAN. But this VLAN ID broadly gives you the opportunity to include the details of the VLAN information within the 802.1Q Ethernet standard. Now, as I was mentioning earlier, here actually this entire Ethernet frame format is given. Here you can see that, as I was mentioning earlier, that first we put the destination address and then we put the source address. Okay, so this is the kind of idea about a VLAN, that means logically segregating a LAN and create a logical broadcast domain on top of the physical broadcast domain. Okay, so this gives basically the overall idea about the switching procedure, which is implemented in the logical, particularly the logical link control sublayer and the MAC sublayer. So part of it is implemented in LLC and part of it is implemented in MAC. This gives you an idea about how this switching basically works in layer 2. Well, so any doubt or any clarification do you want about this switching procedure? Then we'll move to the next functionality. Any doubt up to this point? Okay, then let us move to the next functionality that we are going to talk. It's the error detection and correction. So how do we implement this error detection and correction mechanism and the data link? So ideally, these bit errors can be introduced during the transmission of the signal. It is more common for the wireless network, but it is also possible in case of a wired network. Typically due to the external interference or the hardware or the software fault, such kind of bit error happens. So it is basically you transfer a bit stream and then the things get flipped. Okay, so the bits get flipped and a 1 becomes 0 or a 0 becomes 1. So the question is that how you are going to identify whether such kind of bit error has happened or not while transmitting the data. And one thing you can say that, well, I will use acknowledgement. Although acknowledgement can be used to decide whether certain error has occurred, but typically in a channel like a wireless channel where errors are much more common, in that case, if we just rely on acknowledgement, we are going to waste a huge amount of network resources. So it might happen that in every individual frames that you are transmitting, that frame will contain an error. So that way it is necessary or it is important to implement this kind of error detection and error correction mechanism. And this kind of error detection and the error correction mechanism, we called it a forward error detection and forward error correction. So why we call it a forward error detection? It is something like that whenever you are transferring the data from a source to a destination, you add some redundant information with the frame, and that redundant information will be used to detect whether there is error or not. Okay. So that way you do not need the help of the acknowledgement, rather you can directly do an error detection, and sometimes we will put in more amount of information in the bit, the redundant information. You can also sometimes correct the error up to some level. So these are the kind of methods which we call as the forward error correction. Now, in case of error detection, we include the redundancies so that the receiver can separate out the correct frame and the erroneous frame. Although it cannot identify the actual error, or it may not be able to identify the actual error. And in case of error detection, we include enough redundancies so that the receiver can correct the errors up to certain level. That means detect which bits are having an error. Now let us first talk about the error detecting codes, which are a bit simpler. Then we will move to the error correcting codes. So error detecting codes, the simplest form of it is the parity bit. That means to include a single parity bit with the data. So the parity bit is chosen so that the number of 1 bits in the code word is even or odd depending on the setup. That means we want an even parity transmission and we want to transfer 110.111.0011. Now in this particular data, you can see that we have 1, 2, 3, 4, 5, 6, 7. 7 ones. Now to transfer event parity, to transfer data with event parity, we put a parity bit at the end, which actually makes this code word as event parity. Okay, so the resultant code word is this. So that way, if there are odd number of bit errors, okay, it can be detected. So, for example, if there is a single bit error, it can be reliably detected. If it is a single bit error, then by computing the parity, you can find out this is an odd parity, but you know that any data that is being transmitted from the sender, it should have even parity, and that way you can conclude that, well, there is possibly some error in transmission. Sir, but such kind of mechanism with parity bit, it is difficult to implement for burst error. So burst error basically means when there are errors in multiple different bits simultaneously. Okay. And it is indeed in multiple different consecutive bits. Now, to do that means to support such kind of burst error, the mechanism which is being used, it is called the interleaving parity. So the idea of the interleaving parity is something like this. Rather than adding up a parity bit for every character, you add up the parity bit for a group of characters. So for example, you are going to transfer this word called network. Now n in binary, the ASCII form of n in binary is 1001110. We are using 7 bits binary. Then T is the corresponding binary. T is the corresponding binary. Now, rather than adding a parity bit with K, E, T, W individually, we compute the parity based on this column. So we see that in the first column, everything is 1. So say for example, I want to transmit event parity. So 1, 2, 3, 4, 5, 6, 7. So there are 7 1. So I add up a 1 in the parity bit. Similarly, in the second column, I have 1, 2, 3, 4, 5, 6, 6 ones. So it is already event parity. I add up a 0. Okay. So that way, after transmitting this entire word network, I transfer this computed parity bits. Well, now whenever we are transmitting these parity bits, what will happen that if there is a burst error, so while transmitting, you are transmitting these individual bits in sequence, say in a burst error, you got an error in this this highlighted set of bits. Now, if there is an error in this highlighted set of bits, you can see that you will notice a error in the parity bit as well. Okay. Now that way, you will be able to detect that, well, there is a kind of burst error that has possibly used. Okay. So typically, n number of parity bits are used for k data bits. So that way you can detect the k bit errors, k bit errors with at most 1 error per row. Now again, if there are, we can detect k bit burst error, that means consecutive error in a k bit segment. But if there are more than k bit error, then what will happen that, well, I will have more than 1 error in a single column, and that way it will not get reflected in my parity stream. So for example, here we can detect 7 bit errors. Okay. Now while detecting these 7 bit errors, if I have error in this row as well as in this row, that means in consecutive rows, then 0 becomes 1 and 1 becomes 0, and that way my overall parity remains same in the column. Okay, so that way if there are 2 bits are having an error in a column, that will create a problem for you. You will not be able to detect that. So that way with in parity bits, so we can support k data bits, and we can detect up to k bit error with at most 1 error per row with the help of such kind of interleaving parity, the concept of interleaving parity. Okay. So the third concept for error detecting code, which is much more sophisticated from this parity based things, is the error detecting code in terms of checksum. Okay. So let me explain the idea of this checksum with an example. So let us assume that we are going to compute 16-bit internal checksum. So that means we divide the data into 16-bit words. We use 1 complement arithmetic to compute the sum, and then find out the 1's complement of the result. That's the checksum. Okay. So here is an example. Say we want to transmit this particular data stream. We break it into 2 8-bit words. So we are going to compute 8-bit checksum. Now to compute 8-bit checksum, this 16-bit word we are dividing into 2 8-bit 8-bit words, and then we are computing the 1's complement addition of these 2 numbers. Okay. Now the 1's complement addition that we are getting, well, we are taking the 1's complement of the result, and that is my checksum. Right? So these checksums are more rigorous than parity check. That means if 2 bits are flipped, these things are remain undetected in parity check. We have seen that if 2 bits are getting flipped, then we will not be able to detect that, but you can detect that in checksum. Now, one thing is that as we are moving from the parity bit to the interleaving parity to the checksum, we need to set more amount of redundant information with the data that you can see, right? So that way the overhead is smooth. But at the same time, we are getting more reliability in terms of the amount of error that we are going to detect. So for example, in case of a single bit parity, I just need a single additional bit. In case of this interleaving parity, I need k number of additional bits with k number of data bits. Well, in case of checksum, here you can see that for a 16-bit data, I need to transfer 8-bit additional as per checksum. So that means as you are going with the sophisticated methods for computing the error detecting code, which can detect the errors more reliably, you are actually increasing the overhead data network. You are putting more amount of redundant data with your actual database. So the amount of redundancy becomes more. So that way there is a kind of trade-off between the performance and reliability. If you want your channel to be much more reliable, that way you are actually affecting the performance. On the other hand, if you want less reliability, the system will be more performant. And performance in the terms of the bandwidth utilization by the actual data that you are going to transfer. As you will include more amount of redundant bit, you need to give additional or consume additional bandwidth to transfer those redundant bits. Now the fourth kind of error detection code that we are going to discuss, it is again a bit more sophisticated compared to the checksum. It is called the cyclic redundancy check or CRC. The cyclic redundancy check or CRC, it is also known as the polynomial code. We treat the midstream as a representation of a polynomial with coefficient of zeros and ones. So, for example, this 1 0 1 1 0 0 1 that we can represent as this 1 into, so the first one, that 1 into x to the power 0, then 0 into x square, then 0 into 0 into x, then 0 into x square, then 1 into x cube, then 1 into x to the power 4, then 0 into the power 5, and finally 1 into x to the power 6. So that way, we can represent it in the form of a polynomial and simplify this polynomial. It comes to the x to the power 6 plus x to the power 4 plus x cube plus 1. So that means for the terms, for the non-zero terms, at that position, that means at the 6th position I have an 1, at the 4th position I have an 1, at 3rd position I have an 1, and at the 0th position I have an 1. Okay, so that way we can represent the bit stream in the form of a polynomial. Now this CRC works in this way, that the sender and the receiver, they agreed upon a generator polynomial Gx. That is some initial polynomial that both sender and receiver initially agrees upon. Now for this generator polynomial, there is a constraint that both the high and the low order bits for the generator polynomial must be 1. So that way you can have the maximum term as well as the minimum term present in the generator polynomial. So in that condition, both sender and the receiver agrees upon a generator polynomial apparently. Now to compute CRC for a polynomial, Mx corresponds to a frame. The number of bits in the frame must be longer than the generator polynomial. So that means the number of bits in Mx from which you are going to compute the CRC, the number of bits in Mx must be more than the number of bits in Gx. Okay. So that is another constraint which we have. Now what we do that so that is true for in case of CRC, you sometimes also call it as the checksum. So these are the terminologies which are used in the internet. In some books you will find out that we call it the checksum from computed based on CRC. You have the original message, you apply CRC, the checksum that you are getting, you are appending with the message and sending it. Okay. So you append the CRC at the end of the frame such that the polynomial represented by the CRC included frame must be divisible by Gx. Okay. So that means I have Mx, okay, and I have a generator polynomial Gx. So I generate the CRC checksum in such a way so that the final message that I am going to send, the polynomial representation corresponds to that, must be divisible by the generator polynomial Gx. So that means I am transmitting, say, m prime x. So if I divide m prime x with Gx, I should get a 0 as the remainder. So that means m prime x that I am going to transfer finally, that should be divisible by Gx. Now at the receiver end, the receiver just check whether the received frame is divisible by Gx. If the received frame is, that means m prime x is divisible by Gx, that means you have received the correct frame. Okay. Now this CRC algorithm works like this, that let R be the degree of Gx. So you append R0 bits to the low order end of the frame so that the frame contains m plus r bits, where n is the number of bits in the original frame. The polynomial corresponds to this is x to the power r mx. Now you divide the bit string corresponds to x to the power r mx by the bit string corresponding to Gx using the modulo 2 division, and subtract the remainder from the bit string corresponds to x to the power r mx using modulo 2 subtraction. The result is the checksum to be transmitted. Okay. Now, one thing is that in modulo 2 division, subtraction is equivalent to the XOR operation. Well, so that is one advantage that I have. That means whenever you are doing the subtraction, you can simply do the XOR and you can make it subtracted. So here is an example. Say for example, I want to transfer the frame 1 1 0 1 0 1 1 0 1 1. And my generator polynomial is 1 0 0 1 1. So I have 1 2 3 4 5 bits in the generator polynomial. Well, so what I do that we append that many number of 0 bits at the end. Well, so typically we do 1 minus the generator polynomial so that we append 4 bits at the end. Well, because the generator polynomial has 5 bits, so the value of r is 1 minus the number of bits in the generator polynomial, and then divide it with the generator. Okay, now divide it to the generator means say 10011. So we by taking 1, I get 10011. Now subtract this means the XOR. So 110, 101, 000, 110, 011. Then I take the next bit. Again I make it 1. Okay, because the first bit is 1. So 10011. Then again do the subtraction. So while doing the subtraction, I am doing it this XOR. So 110, 110, 000, 000, 110. I take the next bit as 1. Then it starts with 0, so I take a 0 and make it 0 by doing the again subtraction. I get 00010. Again I make 0, and that way I repeat the procedure, and finally I get this as the remainder 1110. Okay. Now I put this 1110 at the end in place of this 0000, and the finally transmitted frame is this original frame appended with the remainder that we got. It is 1110. 1110. Okay. So this is the final transmitted frame, and you see that this finally transmitted frame is actually divisible by this generator polynomial corresponds to the bit stream of 101. Okay, so that way we compute the cyclic CRC checksum and transmit this CRC checksum along with the data that we are going to transfer. Well, so this is the algorithm which is written here. That you have R be the degree of Gx. Well, so here in this generator polynomial, you see that it is 5-bit long. That means the last exponent will be x to the power 4. So the degree of this polynomial is 4. So you append 4 zeros at the end. Well, so typically it is 1 bit less than the number of bits which are there in the generator polynomial. So that is going to be the degree. So you will append that many number of zeros, and then you perform this division, modulo 2 division, and while doing the modulo 2 division, just remember that subtraction is equivalent to XOR, and that way after doing the division, the remainder that you are getting added to the frame, and that is going to be your final transmitter. Okay. So that is the CRC procedure. Any doubt into this? Okay, then let us stop here today. In the next class, we will start with this forward error correction of the error correcting code. So till now, we have just looked into the code that code blocks that can provide you the detection of number of errors in a bit stream. Next, we are going to talk about the what the way we generate the code works, and that we can also recover from the error. And as I was mentioning, that as you are going with this kind of complex methods which are providing more sophistication in terms of providing you or supporting you in the more number of bits bit error to be detected, you are actually relying on mechanisms or providing more amount of redundancy in your packet. And that way there is a kind of trade-off between the two, the trade-off between the reliability and the performance. So typically the network designer takes this into account. So they think of that which one is much more important. So for example, typically in wired network, where the rate of error is much less, or you will seldom observe a kind of error in transmitting data over Ethernet. So that's why in Ethernet we use simple checksum based method or the CRC based method for error correction. We do not put any kind of error correcting code there. But whereas in case of Wi-Fi, which uses the wireless channel, there are more possibility of having the errors, and that way we put or we use this idea of forward error correction in case of Wi-Fi. Well, but in case of Ethernet, typically we do not use this error correcting code. We are happy with the error detecting code because the possibility of errors are much more less. So that's why we do not go with the complicated mechanism. Okay, that's all for today. So let me know if you have any doubt or you want any kind of clarification. Otherwise, we can keep on our discussion in the next classes.
Sir, this is a bit unrelated, but sir, I had a small request. In the last networks test, what happened was that we had to choose the 4 digits of a roll number, right? So the 5-year students, they had 3,000, and 4-year students had 1,000, which had to be multiplied by 6 and then divided in a way that the difference was less than 100. Now, it was significantly more difficult for 5-year students. So, could you?
Well, I got your query. Actually, a couple of you have already mailed me, and I have replied them separately. So the thing is that if you blindly try to do it, well, 3,000 will be much more difficult from 1,000. Right? But if you do it in an intelligent way, I will share the solution. Maybe by tomorrow or day after, I will share the solution with you. And just because of this reason, I am not going to use any TA for getting it evaluated. I will evaluate it myself. There can be multiple different solutions. All those solutions are possible. So if you do it intelligently, actually at the end of the day, you will find out there is not much difference whether that is going to be 1,000 or that is going to be 3,000. The only thing that you need to keep in mind is that I want to reduce this amount of IP address that are getting wasted and how effectively I can create the subnets. Okay? And that way, once you can solve this part A of the problem, well, so the remaining part are very straightforward. You don't even need to think. Once you have the numbers, you can directly put it up in the corresponding format to do that. And even for the part A, I will actually write it down in details that thought process that you have to apply to intelligently do that solution. Well, if you can apply that, whether it is 3,000 or whether it is 10,000, it doesn't matter. Well, so the point, let me just briefly in one line, let me tell you the point that you should have thought of, and that is the reason I have given this question. See, the constant was that I do not want to waste more than 1,000, more than 100 items in every subnet, right?
Yes, sir.
Now, what can be the maximum number of bits that you can take in any way? Say, if you are going to think of it in this way, say, and the number was something like 8, 2n, 3n, 6n, 8n, something like that, right? So all of these numbers will be something like the multiplication of 1,000, 3,000 or maximum 1,000 to 1, 3,000 to 1, something like that. Well, so that way you can just think of that every subnets will have a maximum number of hosts in the multiplication of 1,000. Well, so by going with that logic, you can see that if I take 13 bit means 10 bit means 1024, 11 bits means 2048, 12 bits means 4096. Now, if you are going to take more than 12 bits for a subnet, well, say in that case, you are going to waste possibly more than 100 number of items, right? So 12 is 4096. So with 12 bits, you can support 4,000 number of hosts, and that way 96 hosts will get wasted from that, or 96 IP address will get wasted from that subnet. Well, but if you go more than that, 13 bit, 13 bit means 4096 into 2. Now, if you just take the lower one, which is multiplication of 1000, you are going to waste more than 100 number of bits. So that is one constraint that I will never go beyond 12. Well, now when I say that I will never go beyond 12, another thing I need to keep in mind that in individual blocks, my IP, my number of hosts, that the number of bits that I am going to put for the host, that should not vary much. That means if I keep the maximum as 12, the minimum I should not keep 8 or 9. Okay, so that way I will face difficulty to allocate the subnet addresses. Well, so that means if it is 12, I will maximum keep it in 10, 11, 12, something in that range. So once you can think of this, then you can easily divide the thing. So if it is 12,000, well, you can get a maximum of 4,000, just make it 4 blocks. If it is 15,000, make 4 blocks or make 3 blocks of 4,000 each. Okay, that gives 12,000 and have 3,000. Okay, and then again break the 3,000 into 2,000 and 1,000. Well, so that way the first part of it you can, means once you have this thought process, the first part of it you can do quickly. So irrespective of what is the number.
Sir, we also had to minimize the number of subsets also, right, sir? So we'll have to start from, if there is a way to separate into 2,
So
then
that concept was not given there. I have said there that you should means you should give priority to the number of IP address hosted. Well, I have never mentioned in the question that you minimize the number of subnets.
So basically, if we can split in a way that the difference is less than 100 by using 3 subnets, we should use 3 subnets, no? So we'll have to anyways minimize it by ensuring the constraint of 100.
No, so so the constraint was given that in individual subnet, you should not have more than 100 hosts.
Okay. And another was that we have to minimize the subsets, right? Subnets, right?
No, that constraint was not given. So that is intentionally I have not put up that constraint, because if I am going to put up that constraint, that is going to make the problem much more difficult.
Yes, sir. So that's exactly what I thought that the problem was.
Yeah, so that is few of you who have this. I was just checking the answer space. Okay, many of you have done that very intelligently, but few of you have put up this additional constraint and made the problem much more difficult. Well, anyway, I understand that. That is just a kind of don't worry that these things are going to affect your grade. So finally, one thing I am going to check that once I am done with evaluating all the answers, just to be fair, what I will do that I will just look into the marks distribution between the this normal BTech and the dual BTech. Well, if I see that there is a significant difference in marks, I will try to normalize that.
Sir, the question states that university has limited funds and you need to minimize the cost.
Yeah, the minimize the cost doesn't mean that you have to minimize the subnet, because you can use a single router with 24 bit and connect all the things to there. So these are the reason I have not put any constraint regarding the routers or any constraint regarding the number of subnets. I have just put the constraint regarding the number of IP addresses.
Sir, it is mentioned that we should not create unnecessary subnets, right?
Unnecessary subnet means, see, the thing is that you should, so it was mentioned in the question paper. Let me just open it. Just a minute.
Sir, I had one more request regarding the final test. Sir, could you separate it into more parts, because I was unable to solve the first question, so I directly lost the 25 marks.
No, do not think that. So that I think I have mentioned multiple times. So do not think that you are going to lose all the 25 marks if you are not been able to solve that. I am going to look into the procedure that you are applying, and if the procedure is reasonable, I am going to do the part working. And that is the reason for this particular problem. I am going to check it rather than giving it to the TS. Because you can rely on the TS for this kind of binary multi, but not for the part multi.
Actually, sir, I was unable to go further than A part due to time constraints. But anyway, sir, I would like the
See, Rahul, understand one thing, right? So all these tests are just to do a kind of relative grading between the students. Well, you are not been able to proceed, I understand that, but I have even found out that it is not like that. None of the dual degree students have been able to solve it. There are dual degree students who are able to solve it. Well, now who are able to solve it, that means they have been able to catch the problem correctly. Right. So that's why obviously they are going to deserve more marks than you. That is the first thing. The second thing is that, as I have mentioned, I am going to look into the marks distribution between the BTech and the dual degree student. And if I see that there is a difference, there is a significant difference between the two marks distribution, then obviously I am going to normalize them. Okay. It's although personally I do not agree that the questions were much more difficult because it is a larger number. It is just because you have not channelized your thought process in the correct direction. Okay. It is the reason for that. But again, I'm going to understand your constraint. This is the first time you are solving such kind of large problem. I was even not given you any kind of assignment or problem statement that you can practice. Just considering that fact, I'm going to look into the marks distribution and the normalize accordingly. Well, so it is. So if I find out that the distribution for BTech and the dual are similar, that means both of them have taken the tests in a similar way statistically. Okay, and there should be no question about that. But if it is different, then obviously I'm going to consider that. And do not worry about the grades. So it is 5 different tests, and finally we are going to do the grading in a relative way. Okay, if you have performed good in other 4 tests and performed poorly a bit in this particular test, well, and if it is the case for the classes that almost all of you have performed good in 4 tests and bad in 1 test, then accordingly you will be graded. It is, and I'm also not going to do the absolute grading like more than 90 CX. Okay, depending on the distribution, even it may happen that 80 gets more than 80 may get TX. So that's why do not worry about the grades or something. Just try to understand the problem statement. Okay, and try to take it a kind of as an experience. Well, so I know that this is a challenging problem statement. Okay, and intentionally we have given that. It is not like that I do not know. Okay, so the question that was given, that do not create the subnets unnecessarily as it will need additional router. Only create the subnets when the number of IP addresses hosted are more than 100. Okay, so that means only when you are seeing that, so you do it in a recursive way. Only when you are seeing that the number of IPs hosted are more than 100, then you break it into the subnets. Okay, otherwise do not create subnets. So otherwise, say for example, the thing that was mentioned, so for example, you have 1000 hosts. Okay. So you can do it 10 weeks with 1024. Well, that means you are wasting 24. So you should not break that 1000 further. Well, so that is the thing. But anyway, we do not worry about these marks and all these things. Well, so as I have told, I understand this is difficult time, and this is the first time you are encountering such kind of difficult problem. Well, let me put the marks, let me put all the grades, and finally, while doing the evaluation, we'll doing the final grading. RSC and myself will discuss together, and we'll take care of it accordingly. Okay. But my intention is that to make all of you to be aware about such kind of problem. So typically in the example that was given in the lecture, that was from the forward direction. That means you have been given the IP address, now you have to create the subnets, and this is in the reverse direction. That you are a network administrator, you need to buy the set of IPs from the network service provider. How will you approach them? So that's all. Just for take it as a learning experience. Do not think that it is going to affect your grade at all. that those things you are going to take care of. We are not going to, I have no personal grudge on any one of you, so I am not going to affect any one of you in the final grade. Okay, any doubt on anything? Okay. Okay, thank you all. So I'm going to share the solution. I'm going to share the solution with 1,000 series, 1,000 numbers and with 3,000. With both the cases, I'm going to share the solution. Okay, thank you everyone. Take care. Bye bye.
Thank you.